Excellent day of plenary sessions, just as good as yesterday. The focus this morning is neutrinos, and our first speaker, Pedro Ochoa Ricoux, a good friend of mine from a long time ago. So over to you, Pedro.
Thank you. So it really is an honor to be here giving this talk. I would really like to thank the organizers for this wonderful invitation to be able to present to you the latest status on neutrino oscillations and CP violation. So just a disclaimer that the field is extremely broad, very, very active. So I had to make some tough choices. My apologies if your featured experiment or result is not covered in this presentation. So let me begin with a short introduction to neutrino oscillations. Neutrino oscillations stem from the principle, or the fact, that the states in which neutrinos interact, namely nu-e, nu-mu, and nu-tau, do not correspond one-to-one to states that have definite mass, which we call nu-1, nu-2, and nu-3. Rather, they're mixtures of each other. This mixture is parametrized by this matrix, which we normally call U, so it's the PMNS matrix, which in turn has three angles, which makes sense. It's essentially a rotation in three-dimensional space, and one CP violating phase delta CP. So with this mixing framework, together with some assumptions about how neutrinos propagate, namely as plane waves, you can predict what the probability is for a neutrino that starts at some flavor to then be detected later at the same flavor, or as a different flavor. These probabilities look something like this, and they always look very similar in that the mixing angles always give us information about the size of the effect, the amplitude, and the delta m squares, which we also call the mass splittings, the differences in the squares of the masses, give us information about the frequency of this effect, how often it repeats itself in this L over E space. So I'm still amazed that this actually happens in real life, but it does, and we have some really good evidence that it does. The first smoking gun came with a Super K experiment in Japan using atmospheric neutrinos. Atmospheric neutrinos, as a reminder, are neutrinos that are produced by the interaction of cosmic rays with the atmosphere. And Super K, which is this large, huge tank of ultra-pure water surrounded by over 10,000 photomultiplier tubes, was able to see that those neutrinos that come directly from above the detector, those came in numbers that more or less matched expectation, whereas those neutrinos that had to go through a sizable fraction of the Earth before reaching the detector, they were in a significant deficit of about 50%. The SNOW experiment in Canada gave us also some beautiful evidence when it showed that electron neutrinos from the sun indeed were in deficit compared to what was expected from the standard solar model, but that the sum of neutrinos from all flavors were in beautiful agreement with what was expected from the SSM. And then I add here the Camland experiment to my list of smoking gun evidences. This is a 1 kiloton liquid scintillator detector in Japan that back then was focused on detecting reactor antineutrinos. And this is the experiment that gave us the first clear evidence that this is really an oscillation. So the neutrinos are not just disappearing, they're reappearing and disappearing, and you get the idea. You see the clear, nice L over E signature for this type of effect. So the implications are huge. If neutrino oscillations do happen, which they do, it means the standard model needs to be extended. And it opens up all of these questions, many of which still don't have an answer. So the first question that comes to mind is, okay, so we have these oscillation parameters, the mixing angles and the delta m squares. What are their values? And we've made some really amazing progress in this regard. Now we know all of these mixing parameters to a few % precision, as you can see here on the right. However, we're not done. We want more. First, we need to determine the octant of theta 2,3, or perhaps if it's maximal, we want to know, because that would point to an underlying symmetry. We want also better precision all across the board. It's important because more precision gives us constraints for other experiments, for flavor and mass models, and to be able to perform model-independent tests of the three-neutrino framework. Another question, this is possibly the holy grail in the field of experimental neutrino physics right now, is whether or not neutrinos obey the CP symmetry. And this, I think I don't have to convince you, we're particle physicists, we want to know if CP is violated outside of the quark sector. But also it could have very important implications in other parts of physics, for example, cosmology. It could give us some hints as to why there's this matter-antimatter asymmetry in the universe. As I will show you later on today, right now we have some indications of CP violation, but none definite. We also don't know what the ordering of neutrino masses is. We know that the second mass eigenstate is lighter than the first one. We know this from matter effects, which I will describe in a second. But we don't know if the third one is heavier or lighter than the other two. We refer to these two scenarios as the normal and the inverted orderings, respectively. Here again, we have some indications, but non-definite, none actually above 3 sigma. We also don't know if there's additional neutrino states. For example, there could be sterile neutrinos. There are other open questions in neutrino physics, but these ones that are listed here, we can address with neutrino oscillation experiments, which leads me to the question, so how do you build a neutrino oscillation experiment? Since we're going to be talking a lot about many experiments, here's a quick overview of how you make such an experiment. So you begin by choosing a preferably strong neutrino source. You have many good choices to choose from, both artificial and natural. Then you sample your flux in ideally multiple locations, or at least one. Sampling at multiple locations allows you to reduce flux uncertainties. Sampling with identical or identically designed detectors allows you to reduce detection-related systematics. And then, very importantly, if the propagation occurs through matter, you need to account for that. The oscillation probabilities are modified by matter effects. This is the MSW effect. And the important thing that I want you to remember about this effect is that it provides us with sensitivity to the mass ordering. So I'm going to be saying matter effects a lot throughout this talk. Once you've collected your data, you fit your observations, and you extract with the model, and you extract the parameters of interest. So what I'm going to do for the rest of this talk is I'm going to show you how traditionally, different types of experiments have been more sensitive to different sectors of the PM&S matrix, as you can see here. So I'm going to discuss these different types of experiments: accelerator, atmospheric, solar, and reactor. And I'm going to show you how they complement and give us this general picture of neutrino oscillations that we have right now. And then I'm going to spend a couple of minutes at the end just discussing those pieces that don't fit into the puzzle, namely the anomalies. So let me begin with accelerator neutrinos. Currently, there's 2 long baseline neutrino oscillation experiments that are currently in operation. So there's NOVA in the United States, and there's T2K in Japan. Both of them follow the same basic principle. You have a beam. Typically, it's muon neutrino. Well, in this case, it's muon neutrinos and anti-muon neutrinos. And the important thing to remember is that you can actually switch between the two. You can have a neutrino beam or an anti-neutrino beam. And then you sample this beam in a location near the source with a near detector or detectors in order to characterize your flux. And then you sample it again in a far location, hundreds of kilometers downstream. These 2 experiments have a similar scope and strategy. They're sensitive to these parameters that are shown here in this yellow box. And as you can notice, this yellow box does include mass ordering and delta CP. Now, as you can imagine, there's a complex interplay of the effects of all of these parameters happening simultaneously. And so we need to be able to disentangle the effects from these parameters in order to be able to measure them. And so the strategy that these experiments follow is to use both nu-mu disappearance and nu-e appearance channels. So nu-e appearance, of course, means that you're looking at those electron neutrinos that were not in your near detector, but that are appearing in your far detector as a result of oscillations, whereas mu disappearance are those muon neutrinos that you had in your near detector, but that have oscillated to other flavors by the time they get to the far detector. And you do this for both neutrino and anti-neutrino mode. The plots here on the bottom right illustrate the power that specifically the nu-e appearance channel has in allowing you to disentangle the effects from mass ordering and CP violation, which is, again, the 2 holy grails right now in experimental neutrino physics. And you can guess from where the data points lie what the preferences for these experiments are going to be vis-a-vis these 2 parameters. But let me just show you more explicitly here in this slide what those preferences are. So at this moment, individually, both experiments prefer the upper octant of theta 2-3 when using reactor constraints. And they also prefer the normal ordering, which I'm going to denote as NO throughout the rest of this talk. The preferences is somewhat mild. We're talking about a base factor of about 3, so it's not definitive, but it's still tantalizing. In terms of delta CP, so the T2K experiment for both orderings prefers this region here of around -pi/2, so the negative side of delta CP. And since, again, this agreement happens in both orderings, then they're able to set a very tantalizing exclusion of CP conservation of 90% confidence. Nova, on the other side, so for the IO, so for the inverted ordering, prefers roughly the same region as T2K. However, for the NO, prefers a completely different region, almost completely different region, as you can see here. A joint fit has been performed by both experiments, and this is something that I think it's great, because it's, I think, the best way to be able to combine experimental results in a way that that handles the correlations between systematics properly. And so due to the agreement here, when the joint fit happens, the constraints on IO are improved, whereas the fit basically splits the difference here for the NO case. So here are the main takeaways from this joint fit, which gives us the state of the art right now in accelerator neutrino oscillations. Let me start here in the bottom left. There's a mild preference for the inverted ordering, but it actually depends on what sets of constraints you use from reactor experiments. Second, in terms of CP violation, there's a preference for this negative side here of delta CP. The constraints are stronger in the IO case, and so that means that if inverted mass ordering is the scenario that nature chose, we are excluding CP violation to 3 sigma. Again, tantalizing, very exciting, but unfortunately we don't know the mass ordering yet. And the other important thing to point out is that these results provide us with the world's best constraints on this parameter, delta m²32, so at the level of 1.4%. So as exciting as this is, I think we agree we need definite measurements. And so we have next generation experiments that are preparing to hopefully give us these definite measurements. And so one of them is DUNE, the Deep Underground Neutrino Experiment, similar concept as NOVA, but with a number of key upgrades. So for example, the beam now is about twice as intense, so we're talking about at least twice as intense, 2 megawatt beam, liquid argon time projection chamber for the far detector technology. So this is going to allow us to look at these interactions with beautiful resolution. The far detector is much bigger. We're talking about a 40 kiloton mass fiducial, and much bigger baseline. So we're talking about 1,300 kilometers. Again, bigger matter effects. You can guess what that means. More sensitivity to the mass ordering. Similar story for Hyper Kamiokande in Japan. So an upgraded beam to 1.3 megawatts and a much bigger far detector. So instead of Super K, now it's going to be Hyper K, which is about 8 times bigger than Super K. So what can we expect from these experiments? In terms of mass ordering, DUNE's going to kill it in a good way. So DUNE is going to basically reach 5 sigma or higher with 1 year, at worst case scenario, 5 years, depending on how kind nature is to us. In terms of oscillation parameters, the 2 experiments, and here perhaps DUNE even more so, is going to give us some really nice measurements, particularly of these 2 parameters, with a precision that's going to be comparable to what we expect to have from reactor experiments by then in the long term. And that's going to enable some really nice, some really stringent tests of the 3 neutrino flavor model. And in terms of CP violation, we expect the 2 experiments in the long term to establish CP violation at 3 sigma over 75% of delta CP values. You can get a little bit more information by looking at these plots. And the plots here on the right just basically show you that both experiments have a similar-ish precision on delta CP. Let's call it better than 20 degrees in the long run. Very good. Now, let me discuss briefly atmospheric neutrinos. So atmospheric neutrinos access the similar parameter space as accelerator experiments. They also have a similar strategy. So this is the same box that I showed you before for accelerator experiments. There are, however, some really nice features in atmospheric experiments or in atmospheric neutrinos that make these experiments highly complementary to accelerator experiments. Atmospheric neutrinos have or allow you to sample a broader energy range, typically, compared to accelerator experiments, and you have longer baselines. And here again, that means bigger matter effects. The panel here on the right illustrates the big, strong signal that you can get, that you can tap onto For example, here there's a comparison between normal hierarchy, inverted hierarchy, or ordering. Sorry, hierarchy and ordering are synonyms, and you can see some significant differences. And these experiments can tap onto these differences in order to measure the mass ordering. So I'm just going to show you quickly the latest and greatest results from atmospheric experiments. Here on the left, these are the latest results from the Super K experiment in Japan. And they use over 6,500 days of data. You can see there's a preference for the normal ordering, as you can see here. And here again, in both cases, you prefer this region of negative delta Cp around minus pi over 2. So it's an agreement with T2K. And actually, there's been a combination that has happened between Super K and T2K. And as you can imagine, this means they can improve the constraints on Cp violation. So that means Cp conservation is excluded to a tantalizing almost 2 sigma. And they also set some limits or some preferences on the mass ordering. They're not definitive yet, as you can see from these p-values here. There's also some really nice results with atmospheric neutrinos coming from experiments where you instrument large volumes of ice or water. So I'm talking about the ICECube and ORCA experiments. And I show you their latest results for the 2 oscillation parameters, delta m squared 3.2 and sine squared theta 2.3, the 2 oscillation parameters that are of interest to, or that these experiments can access. And let me point out a couple of things here. The first one is that these ellipses, you see, they all overlap. So there's really good agreement between atmospheric and accelerator experiments. The other thing to note is that these ellipses have more or less the same size. So there's comparable precision between atmospheric and accelerator experiments. Accelerator experiments have slightly more precision, but atmospheric experiments are getting there. Something I want to highlight is that ORCA is only 20% constructed. So this is actually pretty remarkable, and they're going to be able to improve on this very quickly. So this brings me to this slide, which is that there's a bright future for these types of experiments. In the near term, Super K is going to have improved neutron tagging capabilities because of the addition of gadolinium to the water. That's going to enhance its discrimination of neutrinos and antineutrinos, therefore giving it more sensitivity to the mass ordering. ORCA is going to be built, and ICECube is going to get an upgrade that's going to allow it to be more sensitive to the types of physics that we're talking about here today. In the longer term, of course, we have Hyper K and Dune coming on, which are going to also be able to do some really nice atmospheric neutrino physics. So the main takeaways, I have 2 here. In case you were thinking maybe atmospheric experiments in neutrino oscillations are a thing of the past, that's definitely not the case. These experiments are actually going to dominate. They're going to make some really very important measurements, particularly for these 2 parameters here, theta 2.3 and delta m squared 3.1. They're going to dominate the landscape, as you can see in this plot here, between 2030. And very importantly, these experiments we expect are hopefully going to give us a definite determination of the mass ordering, especially if Juno, which is an experiment I will describe in a second, also has provided some results, because there's some really nice synergy between atmospheric experiments and Juno. Very briefly, solar neutrinos. So solar experiments give us right now the best information we have on this mixing angle, theta 1.2. And this parameter normally is measured with these types of global fits between the solar data as well as CAMLAN's data. CAMLAN, as I mentioned, is a reactor antineutrino disappearance experiment. The agreement is really good between the 2 sets of data, the solar data and the CAMLAN data for theta 1.2. There's a slight 1.5 sigma tension in delta m squared 2.1. This one actually was worse. It was around 2 sigma. So it's getting better. It's something that next generation experiments are going to be able to probe. Now, there's 2 main open questions concerning solar neutrino oscillations, both of which have to do with matter effects, and whether or not we observe the matter effects that we expect in the sun as well as in Earth. And so let me very briefly describe what those 2 are. The first one is this so-called upturn. So we expect the oscillation probability as you go from higher energies to lower energies to increase. And this is because you move from matter-dominated to vacuum-dominated oscillations. We have indications that this is indeed happening, as you can see in both of these plots, but we would like to be able to detect this upturn with high significance. Not only that, we would actually like to be able to map out this upturn because it's highly sensitive to new physics, for example, non-standard interactions. The other effect is the day-night asymmetry. So when you detect solar neutrinos in the day, those neutrinos just basically go through the atmosphere. When you detect solar neutrinos by night, they have to go through the entire Earth before they make it to your detector. And so we expect a few percent difference. And this is now being seen to a really nice 3 sigma, as you can see here. But of course, we want more. So the prospects for solar neutrinos are so broad and so good, the future is so bright, that I'm unable to cover it in detail. I just have one slide summarizing all the great things that we expect will come in the near future. So we have the 3 large experiments, Hyper-K, Dune, and Juno, with complementary abilities about our ability to see the upturn, our ability to measure boron A neutrinos with very, very high statistics, and therefore make some nice oscillation measurements, about perhaps improving some of the measurements from Borexino in the case of Juno. There's also a dedicated experiment in China called Jinping that's also hopefully going to give us some nice information on the upturn. And then there's 2 neutrino detection technologies that could have a big impact in this field. One is Theia, which is a hybrid scintillator Cherenkov detector. And the other one is Liquido, which uses opaque scintillator to be able to have topology discrimination, but also to enable high levels of doping, for example, with indium. So lots of exciting prospects here. Last but not least, reactor neutrinos. So reactor neutrinos, as I already mentioned, give us our best information on this parameter, delta square 2.1 from CamLens, but they also give us our best information to date on theta 1.3. And this comes from these 3 experiments, Diabase, Double Show, and Reno, which follow similar layouts, as you can see here. The strategy for these experiments is to basically measure the first oscillation dip that you see in this plot, which means they need to be at short baselines. So we're talking about baselines of about 2 kilometers or less. All of these experiments use multiple reactors in order to increase the intensity, and multiple detectors, particularly near and far, in order to be able to cancel systematics. And so the 3 experiments have consistent results, as you can see here. Here I just used the results from Diabase as an illustration. So if there were no oscillations, we should be seeing in our far detectors this blue curve that you see here. Instead, we see the black dots. The best fit to the oscillation hypothesis is shown in red. You can see there's a clear deficit with respect to the blue. When you fit this with the 3 neutrino framework, you find beautiful agreement. And so again, these experiments give us the best measurements of theta 1.3 to date, consistent with accelerator experiments, as you can see on that plot as well. And something important to note is that there's currently no foreseen experiment, no confirmed experiment in the foreseeable future that will be able to improve our constraints on theta 1.3, which is why some folks are starting to think of how to do this. There's a proposal on the table for a super show experiment that would be quite different from double show. This one would be in a slightly different location in the same power plant. It would use Liquido technology that I briefly alluded to when I was discussing solar neutrinos. And there's already a demonstrator that's actually funded, that's under construction for this experiment. So it's under exploration. Before any super show would come online, of course, there's this next generation big reactor experiment that's going to start taking data very soon on the scale of a year. It's called Juno, Jiangmen Underground Neutrino Observatory. This is a 20 kiloton liquid scintillator detector, 20 times bigger than any other detector of this type before. And it's going to have a beautiful energy resolution of 3% at 1 MeV. And what that means is that here's the oscillated spectrum that we expect to see in Juno. You can see that with this resolution, Juno will actually be able to see these little wiggles that you can probably barely see, especially if you're sitting in the back, and therefore we'll be able to disentangle or separate or discriminate between the 2 mass ordering scenarios and measure these 3 parameters to an exquisite precision of sub 0.5%, which is about a factor of 1 order of magnitude better than what we currently have, as you see on this table here on the right. Okay, so that leads me to the second part of my talk, which is what about those anomalies, those pieces that, as I said, don't fit with the rest of the puzzle? So let me quickly go through those. You have probably heard of the LSND and mini-boon anomalies. These 2 experiments observed an excess of electron neutrinos, antineutrinos in a muon neutrino, antineutrino beam. And there's no doubt that the anomaly is there. It's highly significant. The million-dollar question is it caused by oscillations, by anomalous or new oscillations, particularly to a sterile neutrino or from a sterile neutrino? There's some data that leads us to say maybe not. And one of those pieces of information is what you see here on the left. If this is indeed caused by oscillations, then we expect experiments like Diabay, like MINOS, which is an experiment, also a long baseline neutrino experiment similar to NOVA, but that ran before NOVA. We expect those experiments to have seen something, but they didn't. And they set some very stringent limits. Also, the microboon experiment in Fermilab, which is a liquid argon TPC, therefore is able to discriminate very nicely between photons and electrons, has been looking for this axis and so far has come up short. They're still looking, so we're keeping an eye out for that, but so far they have not found the axis, or they have not reported an axis. So what's going to happen here? There's 2 more experiments that are going to be able to probe this anomaly very deeply and either maybe put the last nail in the coffin of the oscillation interpretation, the oscillation-only interpretation of the anomaly, and/or hopefully help us understand what caused the anomaly in the first place. One of those is the Fermilab short baseline neutrino program. So this is going to use the same beam that Miniboon used, but it's going to have a near detector and a far detector. Both of them are actually now already running, so it's very exciting. And the fact that it's going to have both near and far detector is going to make it very robust against flux and cross-section uncertainties. The other experiment is called JSNS2. It's in Japan. And it's going to use the same type of source, the same neutrino target, and the same detection principle as LSND. But it's going to have, hopefully, much, much better signal-to-noise ratio. And it's also going to have 2 detectors, one in a near location, another one in a far-ish location. And therefore, is going to be a very definite test of this anomaly. So we're looking forward to these results. As I said, both experiments are already running. So that was one anomaly. There's also the reactor antineutrino anomaly. So this one, let me describe it. Basically, if you go close, short baselines to a reactor, there's a model, or a type of model, called conversion model, the best representative of which is called the Huber-Mueller model, that predicts a certain amount of electron antineutrinos coming out of the reactor. And so if you go and measure that, you find that you come up short by about 6% or so. This is significant to about a factor of 3 sigma, maybe a little bit more now. So what's happening here? I'm not going to attempt to explain this graph in detail. It's a pretty busy graph. I'm more than happy to do so during the Q&A if anybody's interested. But let me just put it this way. The prediction that I mentioned, the Huber-Mueller model, says we should be here. We have a confluence of data that instead suggests we are somewhere over here in particular. So in other words, it looks like the model over-predicted the expected electron antineutrino rate, especially coming from the fission of one isotope, which is uranium-235. And it did so by about the right amount to actually explain the anomaly. So not only do we have a good explanation for why this anomaly occurs in the first place, we also have some null results from experiments that have placed detectors at short baselines from reactors, and they have come up short, with one exception. So there's an experiment called Neutrino-4 that has actually claimed an observation of sterile neutrino oscillations. And that's the point here with the star that you see here, the red contour. All the other experiments set exclusion limits, as you can see here. A few comments about this claim. It is not super significant. It's 2.7 sigma. It is highly controversial. It is in strong tension with the null results from the other experiments, particularly from Prospect and from Stereo. And it does have one thing going for it, which is that it is roughly consistent with the gallium anomaly, which is my last anomaly and my last slide before the conclusions, which is this other anomaly. So this anomaly was first seen by radiochemical solar experiments, so experiments detecting neutrinos from the sun using this reaction that you see here. They were calibrating the detector. Basically, let's put a source of electron neutrinos with an intensity that we know, and let's make sure we detect the right amount. And unfortunately, that did not happen, as you can see here. These measurements were done in the 90s. And so a new experiment was designed. It's called BEST, to test this anomaly. And this experiment actually confirmed the anomaly and strengthened it in terms of its significance. Here again, there's no doubt the anomaly there is highly significant. Again, in my humble opinion, the million-dollar question is, can we attribute this to neutrino oscillations? And there's some difficulties in doing so because of the exclusion contours that I showed you in the previous slide. They're partially in conflict with the space allowed by this, the parameter space preferred by this anomaly. And there's also an experiment called Katrin, beautiful experiment. I'm not able to cover it in detail, but that also sets some limits that conflict with part of the parameter space. So what's going to happen next? There's going to be some new measurements at short baselines from reactors, including from an upgraded neutrino 4. So that's going to be very interesting to see. Katrin also is going to hopefully fully cover the region of neutrino 4, the parameter space of neutrino 4, and most of the parameter space of BEST. And there's some ideas for new tests that are being discussed. I would be more than happy to discuss those over the Q&A. So this leads me to my summary and conclusions. Neutrino oscillations, window to physics beyond the standard model. We know we need to extend the standard model. We have definite questions that we know have definite answers, and we're actively chasing those. We've made good progress, but we're not there yet. We are in a precision era. Most of the data we have collected so far is consistent with the 3-neutrino paradigm, but there are some anomalies. In my humble opinion, it's hard to interpret those as sterile neutrinos, but of course we cannot fully rule out sterile neutrinos. We have this global program with different sources, baselines, technologies. It's going to allow us to explore new territory, and it's going to give us some breakthroughs. And here's a list of what I expect in the coming years. Hopefully, I will not be wrong. I think we will break sub% precision barrier in some oscillation parameters very soon, in a couple of years, starting with Juno. We're going to make, hopefully, a definite determination of the mass ordering within this decade. Hopefully, we'll have a definite observation of leptonic CP violation if nature is kind to us after determining the mass ordering, most likely. I hope I'm wrong. It comes before. And finally, we may actually find evidence for physics beyond the 3-neutrino framework, and that would be also extremely exciting. So stay tuned for more exciting results and hopefully some surprises. Thank you very much.
Thanks, Pedro. Great talk, covering an enormous amount of material, just highlighting the progress in neutrino physics over the last few years. So we have time for a couple of questions. I can see one over there. People will have to jump up and down to be more visible.
Thank you very much for the comprehensive summary. In terms of the anomalies, so in addition to new experiments to confirm or disprove the anomaly, are there ongoing efforts to relook at the old data in the modern view so that to reproduce the old result or find something interesting?
I'm aware of at least one effort, but I'm not an expert because I'm not a mini-Boon collaborator. I'm aware of one effort to look at mini-Boon data now using some machine learning techniques, for example, in order to see if some discrimination can be obtained between electrons and gammas, because mini-Boon is not able to distinguish those two, whereas micro-Boon, for example, and liquid argon TPCs are. And so I'm aware of this effort, but honestly, I could not comment about its status or projected timeline because I am not involved in it. Other than that, so for the reactor neutrino anomaly, maybe I can comment. So as I mentioned, this is most likely due to an overprediction on the side of the model. It's not Huber and Mueller's fault. Most likely, it's a problem with the underlying data. And there's been some really nice measurements done at the Kurchatov Institute that have contributed to our new understanding of why this anomaly occurs in the first place. It would be great if there would be more measurements that would reproduce, you probably know, the ILL measurements that were done back in the 80s that undergird this model. However, I am unfortunately not aware of an effort at this moment that will make this happen, but I think that would be great.
Great. Time for just one more question. Please jump around. There's a hand back there.
Thanks for a very comprehensive talk. I just wanted to know, you mentioned super show. What is the main physics goal of super show?
Very good. So super show's primary goal would be to give us a measurement of theta 1,3 with better precision than what we have right now. So what we have right now in theta 1,3, actually let me be more specific, in sine squared theta 1,3 is 3.2%, sorry, I'm wrong, 2.8%, which is the NGD measurement from Diabet. And so super show would be able to take that down by, let's say, at least an order of magnitude. Of course, it depends on the size of the detector. Now, since we would have also this huge super show detector there's other really exciting things that such a detector might be able to do. And one of them has to do with solar neutrinos. And that's why I mentioned here at the end of my slide on solar neutrinos that Liquido offers some exciting opportunities still to be confirmed. So the technology is in the process of being demonstrated via prototypes. But it offers some exciting possibilities to do solar neutrino detection, specifically via indium doping, the reaction that was first proposed by Raghavan. So those two would be, I think, the main features of Super Show.
Thank you.
Brilliant, thanks. So let's thank Pedro again for that wonderful talk.
Thank you.
So our next speaker is Susanne Mertens, who's going to move on to the physics of neutrino mass rather than physics driven by neutrino mass differences.
All right, thank you very much for the invitation and welcome to this short overview talk on neutrino-less double beta decay and direct neutrino mass measurements. Two of the key questions in astroparticle physics are the neutrinos their own antiparticle, and what is the absolute mass scale of neutrinos? Now, if the neutrino would be its own antiparticle, then the neutrino-less double beta decay becomes possible. And the signature of this decay is a distinct peak here in the energy spectrum of the two beta electrons at the Q value of the double beta decaying isotope. The discovery of neutrino-less double beta decay would be quite a breakthrough in physics, I believe, because it would reveal that there is actually a process where matter can be created without the balancing amount of antimatter. So that may shed some light on the matter-antimatter asymmetry of our universe. It would prove that the neutrino is a Majorana particle, and thus that lepton number is violated. Now, if we assume the simplest realization of neutrino-less double beta decay with a light neutrino exchange, we can also relate the half-life of the decay to the absolute neutrino mass, which in this case is the so-called coherent sum of the neutrino mass eigenstates. Now, what is the challenge? Based on the current limits, we expect less than about 10 decays per ton of material and per year. And that makes it obvious that any future experiment needs a huge exposure on at least a ton scale, a tiny background, and also a very good energy resolution that would allow to narrow down the search window and thus also effectively reduce the background. So where do we stand? This we typically show in this graph that displays the observable, the coherent sum of mass eigenstates, as a function of the lightest neutrino mass eigenstate. And here you can see that the ongoing and completed experiments, they completely probe this so-called degenerate regime where the three mass eigenstates are essentially the same. And here I would like to briefly highlight the new result from Kamlan-Zen. This experiment operates a xenon-loaded liquid scintillator, and its big strength is this tremendous mass of almost 750 kilograms of enriched xenon. And so with their latest data set, they place a limit on the neutrino mass, which already touches here into this inverted ordering regime based on the nuclear matrix element calculation. The planned experiment, they will be designed to fully cover the inverted neutrino mass ordering, where nu3 is the lightest mass eigenstate, but it is important to note that these will also probe a large fraction of the unexplored parameter space, also in case of the normal ordering. So the experimental efforts, they can be divided into these three technologies based on scintillation, ionization, and heat. And here you can see that this is a very active field with many, many experiments, which unfortunately I cannot cover. So I decided to highlight three approaches that were actually considered in a relatively recent DOE review for next generation experiments. So let's get started with ionization, which is realized through germanium semiconductors. And the advantage here is that these detectors can be highly enriched in germanium-76, the double beta decaying isotope. They have an excellent energy resolution, and depending on the specific shape of the detector, one can discriminate signal events from background events based on the shape of the pulses. The leading experiment with this technology is the LEGEND experiment. LEGEND operates currently about 140 kilograms of enriched germanium detectors in an active liquid argon veto system. So with this technique, they reach world-leading performance in terms of background and energy resolution. If you look at this number, this is less than a count per ton and year. So this is quasi-background free, which of course enhances the discovery potential. With their first data release and combined with the predecessor experiments, LEGEND places a limit on the neutrino mass at around 100 milli-electron volts. So while LEGEND continues data taking, the construction of LEGEND 1000 starts, which significantly increases in mass and also further reduces the background. This is designed to fully cover the inverted ordering regime, irrespective of the choice of the nuclear matrix element calculation. Another very interesting approach is based on a combination of scintillation and ionization. And this is realized with a time projection chamber that can be used with liquid or gaseous xenon, which also can be enriched highly in xenon 136. So if you compare this to a scintillation-only experiment, such as Kamlan-Sen, this combination of the signals enables to significantly improve the energy resolution and provides another means to discriminate signal from background. The leading experiment here is EXO 200, which operated a 75 kilogram liquid xenon TPC. They had good performance and eventually placed a limit also on the order of 100 milli-electron volts on the neutrino mass. The collaboration is now focusing on NEXO, and the big upgrade will be here a scale-up in mass to 5 tons of enriched xenon, where part of this is used as a self-shielding. It's also interesting to highlight the advances in barium tagging. So if barium tagging would be possible, one could identify the individual xenon decays and therefore reach an essentially background-free situation. Finally, I would like to present the approach based on heat and scintillation. Here, a cryogenic calorimeter that contains the double beta decaying isotope, this is quite flexible, is operated. And these detectors, they have an excellent energy resolution. And when this system is combined also with a scintillation light detector, again, there is a means to discriminate signal from background. The leading experiment here is Quora, and it operates this impressive amount of almost 1,000 of tellurium oxide detectors at millikelvin temperatures. And recently, they have shown an updated result, also placing a limit on the neutrino mass on the order of 100 milli-electron volt. The next step here is Cupid, and Cupid will tackle this relatively high background index by actually now including a light detector to discriminate this mainly alpha background. Also, they switch from tellurium to molybdenum as a beta decaying isotope. So to sum up, I'm showing you here the results and the projections of those experiments that I have discussed just now. So we have seen that neutrino-less double beta decay addresses both the neutrino nature and the neutrino mass. However, the most direct and model-independent way to measure the neutrino mass is through the single beta decay. In this case, the neutrino mass manifests itself as a reduction of the maximum energy of the beta electron, and thus a spectral distortion of the beta spectrum in the close vicinity to the endpoint. So in this case, we are sensitive to the incoherent sum of neutrino masses, essentially the weighted average of the three masses, and this effect is independent on whether the neutrino is a Dirac or a Majorana particle. The big challenge is that we only have very small statistics close to the endpoint. That means the experiment will need a very strong radioactive source and an excellent energy resolution. And now we are really talking about electron-volt scale resolution, which is not provided by the typical particle detectors. Of course, also low background and an understanding of the shape is very important. So where do we stand here? In this case, we consider the incoherent sum, which explains that these are thin bands and that there is no cancellation. The ongoing experiments, such as Katrin, they fully probe the degenerate mass regime, and the future experiment, they will push this sensitivity into the hierarchical regime. Again, here, the experimental efforts can be categorized in three techniques: counting events above a threshold with an electrostatic filter, a heat signal, or a cyclotron radiation. Also, the direct neutrino mass measurements are a very active field, and I would like to take now a second to highlight a brand new result from the Katrin experiment. So Katrin, in a tiny nutshell, the 70-meter-long beamline here combines a super high-activity gaseous molecular tritium source with a high-resolution spectrometer, which only transmits electrons above a certain threshold, which is given by the voltage on this spectrometer. So by measuring the rate as a function of the voltage, we obtain the so-called integral beta spectrum from which we can infer the neutrino mass. So just 2 weeks ago, Katrin released a new result, which is based on 250 days of data taking or 5 measurement campaigns that you can see here. And on the bottom, you see the corresponding integral beta spectra. From our fit, we obtain a slightly negative value for m squared, which is completely compatible with 0. So we place a new limit of 0.45 electron volts. And this is almost a factor of 2 better than the previous releases. The final goal of Katrin will be to reach a sensitivity better than 0.3 electron volt. So now the question is, how can we go beyond Katrin? How can we go to better sensitivity? And one key ingredient is to switch from counting electrons to actually perform a differential energy measurement, meaning measuring the energy of each individual electron with high resolution. And one approach here is the cyclotron radiation emission spectroscopy. Here, the energy of the electron is measured through the frequency of the cyclotron radiation that it emits when it's trapped in a magnetic field. And this approach was invented by the Project 8 collaboration, and they showed that this actually works, and they also set a first limit on the neutrino mass based on a small statistics tritium run. The next step, and also the big challenge, will be to scale up from cubic centimeter traps to cubic meter traps and also operate multiple of them. Eventually, they are going to use atomic tritium, which would avoid some molecular effects. Another way to perform an electron volt scale differential measurements is based on the low temperature microcalorimetry, and this technique is ideally suited to be combined with holmium as a radioactive source. The holmium decays with an electron capture, leading to this line spectrum here. And interestingly, when we zoom in to the very low endpoint, we can see that also here we see the effect of the neutrino mass very similar to the case of tritium. The 2 experiments that are exploring this technique are ECHO and Holmes. And they have recently shown an updated result on the neutrino mass based on small prototype detectors with about 50 of these microcalorimetry pixels. The next step, and also the big challenge, will be to scale up. And in order to reach a sub-electron volt sensitivity, on the order of maybe 100,000 or 1 million pixel will be needed, which is, of course, quite a challenge to operate in a cryogenic environment. So with that, I already come to my summary and conclusion. The neutrinoless double beta decay and single beta decay are unique and complementary probes of the neutrino mass and the neutrino nature. This is a very active field. We have seen many new results recently. Let me highlight again the first data release of Legend 200, an impressive new result from Kamlan Sen, and a new world-leading limit on the neutrino mass from Katrin based on a direct measurement. There is very high discovery potential for the future neutrinoless double beta decay experiments in, let's say, the next 10 years or so, and there are some very interesting technology advancements that could eventually allow for a direct measurement of the neutrino mass. And with this, I would like to thank you for your attention.
Thanks, Susanne. Great talk, and congratulations on the Katrin result.
Thank you.
Very, very impressive. We have time for a couple of questions. Stefan.
Thanks for the very nice overview of both these exciting topics. For both neutrinoless double beta decay and direct measurements, the experiments you show are basically sensitive to the inverted ordering. As we learned in the previous talk, we might have a resolution of that question of the timescale of about 5 years,
yes,
and it could be the normal ordering. So how would you see this going forward if the normal ordering proves to be
Thank you very much for this question. I would love to comment on this. So I think the answer is twofold. So the first thing to note is that, let me just stay here, is to note that the future experiments, they are also still probing a large fraction of the unexplored parameter space in case of the normal ordering. So you can do some statistical analysis, and the discovery sensitivity is still, depending on your assumption, at 50% or so. But maybe the more important point here is that the relationship between the half-life and the neutrino mass only holds if you assume the simplest process of the light-neutrino exchange. So if there is new physics, then this relationship changes, and then it makes much more sense to talk about, to think of these experiments as experiments to search for new physics in terms of lepton number violation with an unprecedented sensitivity, irrespective of the neutrino mass. So we show this graph because it is an easy way to compare the experiments, but really these experiments are looking for lepton number violation.
Thank you. Any other questions? Again, you have to wave your hand wildly. Oh, there's the wild hand.
Yes, I was wondering a little bit on a different view. I mean, which technology and which you will think that is more scalable to get, to the experiments that you will need to get to the normal ordering?
Yes. So, I mean, you can see here that these experiments are performing, I mean, they all have their pros and cons, and it's very difficult to really pick out one and say this is superior over the others. So you have seen with the germanium detectors, you have really good background performance and energy resolution. It's a little bit more difficult to scale up because it's individual detectors, but it's possible. For the liquid xenon, you can go to a relatively large mass. However, it's also not so easy to procure so much enriched xenon. And so this approach here with the cryogenic calorimeters can also be scaled up. So right now they are considering to use the existing cryostat, but there are plans to scale this up. So I would not say at this point that there is a clear favored technology to go for the ton scale or even multi-ton scale.
One final question over there.
Well, it's related to what you just said. You almost answered it. It just seemed to me that when you talked about the future, you said you could use new ideas to go below this, well below this 0.45 that you reported. But how you didn't say how far you could go. It's sort of related to what she was asking. You know.
Okay, let me just. It's a bit. So here, for example, Project 8. You can see here a sketch. So it plans to operate these large-scale, large-volume cavity resonators that would contain atomic tritium in a sort of magnetogravitational trap. And so in their design, they are envisioning to operate multiple of these traps. And in this case, they would reach 40 milli-electron volt sensitivity. So that is below the inverted ordering. And that's kind of, I mean, that's the natural next step to cover this inverted ordering regime. So typically, the experiments are designed in a way to reach this next step.
Brilliant. So we've run to the end of our time, so let's thank Susanne again for a wonderful talk.
Thank you.
Okay, so let's welcome our next speaker, Lulu. She will tell us the exciting searches for astrophysical and cosmological neutrinos.
Thank you very much. Thank you very much for the kind invitation. So I'm going to talk about searches for astrophysical and cosmological neutrinos. So the sources usually we talk about are astronomical scale. So for instance, this M87 is a supermassive black hole that's located 50 million light years away from us. So that means neutrinos and photons will have to travel all the way to us. And in fact, they were created even earlier than the very first human being on this planet. So when you look at the M87, you see this jet coming out from the black hole. So this is visualized from the Hubble telescope. This is a plasma. So you can imagine there's an accelerator of the scale of about 5,000 light years. So just to scale, that's about 3 billion times the distance from Earth to the Sun. So particle astrophysics essentially is to look through history of cosmos via particles. You might be familiar with the CMB map, the Cosmic Macro Background Photon Map. So that traces back all the way to the Big Bang. And you can go to higher energies. So this is the gamma ray map, so from the Fermi Gamma Ray Telescope from NASA. And you see this distinct bubble shape. So these are so-called Fermi bubbles above and below our galaxy. However, when you want to go to even higher energy photons, the universe becomes opaque. So that's because the photons will interact with CMB photons and have this simple pair production to attenuate the high energy photons through the universe. So when you want to go to the very high extreme energy like PeVs, the photons can only travel as far as from the center of our galaxy. So that's why it becomes very important that we need to use neutrinos or alternative messengers to study the highest energy phenomenon from our universe. So there's a certain beauty in the universality of particle showers. So here is a cloud chamber picture of a proton of a 1 TeV going through the light plates. And on the right, so this is a particle shower in the atmosphere. When you have cosmic rays interact with atmosphere, generate thousands, hundreds, and thousands of secondary particles that can be detected on the ground and also seen in space. So what we want to measure essentially is the neutrino flux. And we're really interested in the region of the very highest energy. So before we reach there, first you have a background of atmospheric neutrinos. So this is basically what we just talked about, the air shower. You have a cosmic ray interact with the atmospheric particles, and you can generate hadronic interactions. You have the pi plus, pi minus, which essentially create neutrinos. So the signals we really want to measure are these neutrinos from AGNs of other sources. So you have a supermassive black hole, you have jets, you have hadronic interactions, and you also have these neutrinos created from the hadronic interactions. So the last category of signals we want to find are the cosmogenic neutrinos. So these are ultra-high energy cosmic rays of 10 to the 19 electron volts interacting with the CMB, the cosmic microwave photons. So they would create a delta resonance, and you can see the decay product of the neutrinos from this very highest energy interactions. So this is almost a guaranteed flux because we know ultra-high energy cosmic rays do exist. So to measure this GeV to EeV scale of neutrinos is certainly not a simple task. So at the lowest energies, usually we go to underground experiments, so we can build a detector in a very nice control environment, and those usually are targeting at below TeV. Once you want to go to TeV to, let's say, PeV, you need to use much larger instrumentation volume because the flux flows as parallel. So in this case, it's very hard to make just a man-made environment, so that's why we start to use nature as part of the detector. So usually we build our detector underneath the ice or underneath the water. And at the highest energies, because photons would attenuate in the transparent medium very easily, so it's harder to scale up this type of detectors to the highest energy detections. So that's why we need to find alternative methods, such as using radio or air showers. So this is usually for the larger than 50 PeV detections. So this is the landscape of neutrino telescopes on the planet. So the red dots, so these are the astrophysical detectors. So we have ICECube here down south in the South Pole, and we have the KM3NET Antares telescope in the Mediterranean Sea. So this size is going to be 1 cubic kilometer, similar with IceCube. Currently, they have deployed 28 out of 230 strings. And then there's Lake Baikal in Russia, so this is also in the construction phase. And then there's the P1, the Pacific Ocean telescope. So this one is in the planning stage, prototyping stage. And then there's a bunch of telescopes proposed by China in South China Sea. So these are also in the prototyping stage. And the green dots, so these are the proposed and current running observatories for ultra-high energy neutrino searches. So I'm going to focus a little bit on IceCube because this IceCube has been running for the past decade. We have many results, and so IceCube detectors is located at the South Pole. So we drilled 86 holes beneath the ice of South Pole, and this is to scale. So this is the size of Eiffel Tower, and this is the size of the detector. So we drilled down the about 3,000 meters below the surface. So embedded in the ice, we put photomultiplier tubes hosted by this dome. So it's called digital optical module. And it was completed in 2011. And typically, we have the up rate about 99.7 to 99.9%. And so far, only 36 dome failures since the commissioning. So that's because in the Antarctic ice, it's extremely cold, and it's very friendly for the electronics. So very soon, in 2026, we're going to deploy IceCube upgrade for neutrino physics and for ice calibration. So we're going to introduce these two types of new sensors, the M-dome. So this is inspired the KM3NET design, and the D-egg, which has PMTs looking up and down. So what we measure in IceCube are the charge current interactions and neutral current interactions. So charge current interactions, you see a track from the muon neutrino and a cascade from electron neutrinos. And for the neutral current, you see all the events as a cascade. And also, we're sensitive to the glacial resonance event, which I'm going to talk about later. So after 10 years operation of IceCube, we managed to put diffuse astrophysical neutrino flux on this diffuse map. So here on the x-axis is energy, y is the flux times E squared. So this blue is from the Fermi telescope for the gamma ray measurement, and green is the ultra-energy cosmic ray measurement from POG. So before turning on IceCube, this range was completely blank, and now for the first time, we are able to put neutrino constraints on the diffuse flux of the highest energy phenomena in our universe. So here what's really interesting is the energy density of the three messengers are comparable. So you see, usually when this happens, it means these three species could potentially be generated from the same type of origins. And that's really what we're very interested, whether the neutrinos were created from the same sources as the ultra-high energy cosmic rays. So the highest energy neutrino we have observed so far is a muon neutrino that has the interaction vortex from inside the detector. So it's very clean, it's not atmospheric muons. And the energy deposited is about 4.8 PeV. So d over dx is about 1 TeV per meter over the last 400 meters. And from resimulation study, we conclude the neutrino energy is likely to be 11.6 plus minus 2.6 PeV. So because this event is from the southern hemisphere, so that means if it was a neutrino event from the atmosphere, it should have been accompanied by the muons that from the same shower. So the fact that we don't see any charged muons from this event, it means it's not it's not atmospheric neutrino, but this we're very sure is of astrophysical origin. So recently, there's a really intriguing result from KM3net that was reported in Pascal's talk. So they observed this very high energy neutrino that's recently detected in the KM3net detector, even though it's only partially completed. In fact, they calculated, I don't know why this didn't show up, but they calculated the energy distribution, and they concluded that the energy of this event is likely to be 100 PeV. So please check the updated slides. Probably something wrong with the PowerPoint. So it's really interesting and exciting because if this is true, then it will be ultimately the highest neutrino that we ever detected from any neutrino telescope. So I believe some paper has been planned to follow up, and we're very interested in looking at details such as the probability of rejecting background. So essentially, we use Earth as a target. So when you have very high energy neutrinos, the neutrinos would not penetrate through the Earth because the cross-section increases. So the inverse of that, we can make a measurement of the neutrino nucleon cross-section. So this is basically the data points from ICECube measurements. You see it's a nice extension of the accelerator neutrino measurements, such as from phasor. And this is the future projection with ICECube Gen 2. We also measured a W boson glass resonance candidate. So this event, this is really an event view that resimulated with photon retracing. So here, each line here shows actually how the photon propagated, and you see this very nice shower in front. So this is from the muons that's produced in the hadronic jet that come from the W boson decay. So this is essentially an on-shell W boson resonant production, and it happens when the neutrino energy about 6.3 PeV, and that's precisely what we have seen. We can also do neutrino flavor calculations, so flavor triangle constraints. So the tau neutrinos would first be produced and would eventually decay, so you expect to see double cascade structure in the tau neutrinos. So by identifying tau neutrino candidates, we're able to set constraints on the flavor triangles. So very soon, we'll have a new result that you can see the 1 sigma contour actually is closed. So please just keep tuned between to that new result. OK, so we also can do forward charm measurements. So the forward charm is very important background for astrophysical measurements because usually they're generated from cosmic ray interaction. And once the charm particles produce, they will decay immediately, generating very high energy neutrinos, which essentially is what we measure at the energy range of astrophysical neutrino. So this is from neutrinos from the conventional, so kaons and pion decays. And this is as a comparison, it's an electron charge current interaction that detected by phasor. So we're very excited about the potential capability that phasor could offer in terms of the forward charm constraints. So we can put those in our fit when we calculate the astrophysical neutrino flux. So for the first time, so this is also not showing here. So for the first time, we actually be able to constrain the normalization of the prompt neutrinos with non-zero result. So we have actually measured a prompt normalization that is larger than 0. And although at 1 sigma is still consistent with 0, so we set Feynman-Cousins limit here. So you see this red line is here, and this is astrophysical spectrum. So now maybe you can understand why prompt is very important background for ICECube neutrino results. So the brightest spot in sky after 10 years of data taking is here. So that's consistent with the position of NGC 1068. So that's a supermassive black hole that does not have a jet. So the poster trial global significance is about 4.2 sigma, and we detected 79 plus minus about 21 neutrinos from that direction. So what's really interesting about this black hole is that we did not observe gamma rays from this source. So we saw neutrino flux here, but the gamma ray flux is upper limit. So this could be because this, the supermassive black hole is actually surrounded by very heavy matter. And when gamma rays try to escape, they will simply just be attenuated or absorbed. So this also illustrates the importance of using neutrinos as a tracer to study the highest energy interactions that close to the center of the black holes. So right, we waited 10 years for our first source of more than 4 sigma. To be able to accelerate our discoveries and to understand the sources of particle physics, we really need more sources. So one way to do that is to develop a new detector. So we have a proposed IceCube Gen 2, which is about 8 times the size of IceCube. So once we turn on the IceCube detector, 2 years, we'll be able to detect the NGC 1068 black hole with more than 5 sigma. And with 10 years of data taking, we can reach 10 sigma. So IceCube Gen 2 will also be able to increase our sensitivity to the highest energy neutrino region. So for instance, when you have ultra-energy cosmic rays, many models suggest that you will produce neutrinos of energy about 10 PeV. So this is from the p-gamma interactions at the source. So currently, our measurements is completely driven by statistical uncertainties. But with IceCube Gen 2, you'll be able to see much narrowed error bars, and we can have a very nice constraint on such models, for instance, to connect to ultra-high energy cosmic rays. So the ultra-high energy neutrinos are very difficult to detect. We still have not seen any. There are many different experiments have been proposed in the next decade. So for instance, the Ascarian radio array uses Ascarian radiation in ice to see these highest energy neutrinos with radio detectors. And you can also use mountains to interact with tau neutrinos, and you can put some radio detectors here to see the secondary showers from the tau decays. And you can also see that with air Cherenkov detectors, and you can put telescopes in space to look down to the atmosphere to see the showers from neutrinos. Or you can use moon as a target, put your radio telescope beneath the moon, and the neutrino will interact with the moon and create Ascarian radio array, radio emissions that you can detect on the surface of Earth. So there are many different experiments have been proposed, and we summarized in our recent SNOWMAS paper the high energy and ultra high energy neutrinos. So for instance, this line here is the sensitivity we expected from IceCube Gen 2, and this is from the GRANT experiment, which proposed radio detectors in China. Okay, so there is certainly a risk to the ultra high energy cosmic ray puzzle, so please check out this paper if you're interested. So that brings me to my conclusion. Through the past decade, IceCube has achieved many groundbreaking discoveries. We discovered astrophysical diffuse neutrino flux. We established NGC 1068 as a point source obscured in gamma rays. We have detected a candidate for glass resonance, and we have conducted flavor measurements and identified tau neutrino candidates. We found evidence for neutrinos from the galactic plane, which I did not cover. So you see that for the first time, the galaxy is visualized not in photons, but in neutrinos. We also detected neutrinos exceeding 10 PeV. So the future is definitely bright because we have so many experiments proposed for the next decades to come. So the coverage will be from TeVs to EeV energies, and the experiments would range from underground detectors to space missions. That's all. Thank you very much.
Okay. Thank you for this very nice and comprehensive overview. Let's take questions there.
Thank you very much. When we talk about the neutrinos that several tens or hundreds of PeVs, how do we assign the uncertainty to the measured energy?
Yeah, that's a great question. So I can speak for IceCube here. So this event, you see this event start from the center of the detector here, and we see the first interaction. This is from the hadronic jet, so you have a charge current interaction. And then we also see how the muons develop in the detector. So dE over dx scales with the energy of the muon, and then we can run resimulations to match neutrino simulations that exactly agree with the pattern we observe here. And then we also have systematics in the detector to accommodate, so that's basically how we derive this number.
Okay, a question over there.
I wanted to ask you, how many tau neutrinos did you observe so far with ICECube? These tau neutrinos are interested, for instance, to look at intrinsic charm. We recently realized that tau neutrinos are very important to measure intrinsic charm contribution, which can be very forward and measured by phasor, for instance.
Mm-hmm. Yeah, that's a good question. So the tau neutrino we detect actually is much more than what we show. So usually we show a few candidates because they're clean events. So you can differentiate those tau neutrinos from the background. But intrinsically in our detector, of course, we measure hundreds of thousands of neutrinos, and a third of them, if it's astrophysical origin, should be tau neutrinos. So I think the question here is how easy can we identify individual tau neutrinos? So far we have 7 candidates that have this distinct double pulse structures. But yeah, so in principle we have a lot more of them in data, we just don't know which events are.
Okay, so last one, Dimitri.
Thank you for a very nice talk. So you mentioned many upgrades and new experiments for these ultra-high energy neutrinos. Can you say a few words about the timeline, when these experiments even potentially can get to data taking?
Yeah, so for the astrophysical experiments, so for instance, KM3net, I believe the spokesperson is here, so they have deployed 28 over 230 strings, so they're about more than 10% completion. I believe they aim at completion, total completion by 2028. So the P1 experiment is in the really the beginning of the phase. They are going to deploy the first few strings in the next few years. So this Trident and the Chinese experiments, they are also the gigantic size. They're also in the very beginning to test the water, how clean the water is, and that kind of R&D stage. As for the IceCube Gen 2, so we're fully funded for the IceCube upgrade, but we have not moving forward to IceCube Gen 2 at this point, but we will try very soon. And then for the cosmogenic detections, so you have Trident, also, sorry, for the cosmogenic, you have the Grand experiments. So this is also prototyping. You have all this, basically, Bacon is going to fly very soon. Trinity is, at the moment, they built one small telescope that have not scaled up. And so ROG is actually in data taking already, but they are also trying to complete their deployment. So I would say next 10 to 20 years. Fingers crossed. No more COVID.
Okay, so let's thank the speaker again. Thank you. And then let's move to our theory talk given by Raymond Volkas. He will give us an overview on the neutrino theory.
Okay, good morning, everyone. It's my honor to be giving this talk, and I thank the committee for the kind invitation and also the opportunity to explore this fascinating city. So a change of tack, I'm going to be talking about neutrino theory. Here is my official title, and I'll give you my real title in a few seconds. But before that, I just want to point out that there are a whole lot of very interesting and important topics in neutrino theory that I do not have the time or even, in some cases, the qualifications to cover. So you can read them here, but let me just point out that there are many excellent slides on these topics and other topics from the parallel sessions here, and also from the relatively recent Neutrino 2024 conference. Okay, so here is the real title of my talk. It's called The Quest for Understanding the Origin of Neutrino Masses. So first of all, this word quest. So I went to the dictionary. Here we have Britannica. So it's a long and difficult effort to find or do something, a quest for answers. And an example of its use is he refuses to give up his quest to discover the truth. So I think we can say that we are on a long quest to uncover the origin of neutrino masses. Maybe we'll get there, maybe we will not. We have to see what the future has in store. Of course, quests have been talked about in different contexts for some time. So here we have a very famous mythical quest, the quest for the Holy Grail, and here is Sir Galahad, guided by an angel, looking for the Holy Grail. And in the case of the Holy Grail, it's not even clear what the thing is. Most authorities agree it's a cup, but they're not even sure if it's a cup. So there's a quest for something that doesn't exist, and they don't even know exactly what it is that doesn't exist. So quests can be funny things. Here's another one, Don Quixote. Here's Picasso's version of it. And this is the mad quest to revive chivalry. So chivalry is a well-defined goal, but it's kind of insane to try to do that. So quests are tricky things. So what is our quest? Here I give you the standard model Lagrangian in all its Byzantine glory, with massless, but it's the minimal standard model Lagrangian, so it has massless neutrinos. And so what we want, our quest, is to find additional physics that we can add, perhaps, to this Lagrangian that will tell us the origin of neutrino mass and that we can write in the textbooks. So, in reference to the previous quests, are we hopeful like Sir Galahad? Are we going to be able to find out what this ... is? If so, what angels will guide us? Or are we mad to try it? Are we mad like Don Quixote? Before embarking on an exposition on this, let me point out that expressing this as an addition to the minimal standard model Lagrangian may or may not be correct, because there are important aspects of this physics that have yet to be confirmed. The Higgs self-coupling, we've had a lot of fascinating talks about that here. That's got something to do with the origin of mass, which the neutrino mass problem is part of. But perhaps more directly, we haven't confirmed most of this Yukawa Lagrangian yet. And this very directly pertains to the origin of mass. So it could be that our quest is a little more complicated than adding something to the minimal standard model Lagrangian. Maybe we will need to change some aspects of this, particularly in the flavor sector, in order to achieve our goal. We shall see. Okay, so here is the structure of my talk. First of all, I'll explain why new mass is new physics. I'll then explore the question of whether new mass implies a new mass scale in nature. Then I'll go through a number of reasonable possibilities for how neutrino mass may be generated and comment on our potential for discovering these scenarios, tree-level high-scale seesaw models, low-scale seesaw models at tree level, and then loop-level models. Okay, so first of all, neutrino mass. The discovery of neutrino mass through neutrino oscillations is the discovery of new physics. Let me explain quickly why this is the case. In the minimal standard model, we have no right-handed neutrinos, and we also do not have a y=1 scalar triplet. And this implies massless neutrinos and family lepton number conservation. Now let's switch on neutrino masses. We know that neutrinos may be Dirac particles or Majorana particles. Suppose they are Majorana particles. In that case, it's the first Majorana fundamental particles discovered, and that is definitely new physics. Also, in order to generate Majorana masses, there are a plethora of mechanisms, and they always involve new degrees of freedom, and new degrees of freedom are new physics. On the other hand, if neutrinos are Dirac, we know right-handed neutrinos need to be added, and these are new degrees of freedom, and that is new physics. And also, in the case where right-handed neutrinos are gauge singlets, as they are in the standard model, that means that there's a renormalizable term that we could write in the Lagrangian, which is a new R Majorana mass, that we don't write. And that means we're imposing lepton number as a symmetry, and this is the new principle. One way or the other, the discovery of neutrino mass implies new physics. So does it imply a new mass scale? So we've seen this week this beautiful new powerful bound from Katrin on the mass scale of the neutrino. If we use cosmology, it's more model dependent, but we get an even stronger bound of about 0.1 eV. So let's call 0.1 eV kind of the scale of neutrino mass. So here it is on a logarithmic plot compared to the other fermions, and we see that neutrinos are much, much, much lighter. Notice that there's this interesting confluence with the dark energy scale, but never mind, we won't talk about that. All right, so is this very light, are the very light neutrino masses associated with a new scale in physics? Well, suppose it's not a new scale, then what would that mean? So we have to face the fact that then, even though we're not talking about a new scale, the neutrino masses are still observed to be extremely small. They're bounded to be extremely small, much smaller than any other known non-zero particle masses. And we can accommodate that in a very simple way with a Dirac neutrino, which implies a Yukawa coupling or a bunch of Yukawa couplings of order 10 to the minus 12. Now, 10 to the minus 12 is a very small number, but if we believe the standard model account of how all the fermion masses are generated, we already have to live with some small parameters. In particular, the electron Yukawa should be about 10 to the minus 6. So you can ask yourself, or we can ask each other, is 10 to the minus 6 okay as a parameter? Technically it's okay, but do we really like it? Do we find that compelling? If we find that compelling, is another factor of 10 to the minus 6 also okay? So we get to 10 to the minus 12. Of course, no one knows the answers to these questions, but many people are suspicious about 10 to the minus 12 as a remarkably small number, and some people, like me, are even a little suspicious about 10 to the minus 6. And in fact, as a side remark, with Baker and Cox, during the pandemic, we showed that even the B and the tau masses may have a radiative origin, not the standard model origin. So, you know, the origin of all the fermion masses is an ongoing, very interesting question for us to think about and explore. All right, for the rest of this talk, I'm going to suppose that the mass scale of neutrinos does imply a new mass scale in nature, and that I will also specialize to the case where the neutrino is a Majorana particle, that is, it is its own antiparticle. So model building in this domain is dominated by two questions. One is explaining why neutrino masses are so small, and the other, in the case of Majorana neutrinos, is what is the origin of lepton number violation. So now let me go through some well-studied, reasonable possibilities. So the first one are tree-level, high-scale seesaw models. There are many talks that mention these ideas. This idea dominates our thinking about theories of neutrino mass generation. Now, there's an interesting and well-known fact that if you write down the lowest mass dimension, non-renormalizable gauge invariant operator in the standard model, which is the Weinberg operator, there's a direct connection with Majorana neutrino masses. So the Weinberg operator has two lepton doublets and two Higgs doublets. There's a scale of new physics, capital M, and some dimensionless parameter lambda. And if you stick in the vacuum expectation value for the Higgs, you immediately get this famous seesaw formula, where the neutrino mass is related to V squared over capital M, and in the limit where capital M is a high scale of new physics, higher than the electroweak scale, you explain why neutrino masses are tending to be very small. If you put some numbers in, put 0.1 eV for the neutrino mass, the Higgs VEV, you get a mass scale of new physics of 10 to the 14 GeV. This is a very, very high scale, and it is quite a compelling scenario, but unfortunately the testability of this scenario is very low. Not only is the scale very high, but as we'll see when we start to open up this operator and look at the underlying theory of it, we may also have extremely weakly coupled particles. Okay, so here is the Weinberg operator in graphical form. And one thing we're interested in is what underlying physics gives rise to this operator at low energies. And if you open it up at minimal tree level, you get these three famous possibilities of the type 1, type 2, and type 3 seesaws. This one involves just right-handed Majorana neutrinos. This involves a scalar triplet, and this involves a fermion triplet. So the type 1 seesaw model is, I guess, the favored one, the most studied one. So its features are the mediator is a massive, or a bunch of massive Majorana right-handed neutrino gauge singlets. As I've said before, if the scale is very high, this is untestable. That's sad for us, but it has a great advantage. As pointed out by Fukugita Yanagida a long time ago, you can explain the baryon asymmetry of the universe through leptogenesis, through the out-of-equilibrium decays of these heavy Majorana neutrinos. Interestingly, the same Lagrangian, but with much smaller right-handed Majorana masses, which is called the new MSSM, invented by Shapozhnikov and collaborators. This is also interesting. Same Lagrangian, but a completely different parameter regime. For type 2 and type 3, the mediators have electroweak quantum numbers, so that means their experimental prospects for detection are greater than just gauge singlet nu Rs, but because generically you expect the scale to be rather high, I wouldn't say the prospects are still great. Nevertheless, for example, the type 3 seesaw mechanism has been searched for by ATLAS and CMS, and there are bounds. Some comments on the type 1 seesaw mechanism. I would say at the standard model gauge group level, the type 1 seesaw mechanism is very obvious and very compelling. All you do is add gauge singlet right-handed neutrinos, which is a terribly obvious and very aesthetic thing to do. And you use the most general renormalizable Lagrangian, which is, you know, a great guiding principle of modern model building. So standard Yukawas and right-handed neutrino Majorana masses. And you get leptogenesis as a wonderful byproduct. Something less well known, but I'm very interested in, is you can actually identify the seesaw and Pechet-Quinn scales and therefore have a connection with axion physics, strong CP, and so on. Now, is there any reason to perhaps doubt the compelling nature of the type 1 seesaw? Well, one thing I can point out, I mean, it's not definitive, but one thing you can say is that when the right-handed neutrinos are embedded in some extended theory, in a non-trivial gauge multiplet, so they're not singlets like they are in the standard model, then you're having to deal with scalars in higher dimensional representations in order to give those things Majorana masses. You can no longer just give those things Majorana masses at tree level in the Lagrangian. You've got to get that from symmetry breaking. So in this case, it implies a connection with gut breaking or some higher symmetry breaking, but it also implies higher dimensional representations. So for example, for SO10, you need to use the 126-dimensional irreducible representation. You may like that or you may not, but if you want smaller multiplets, then there is an alternative. And that leads me into tree-level low-scale seesaw models. So here what you do is, in addition to a right-handed neutrino, which is now embedded in some gauge multiplet in many of these theories, you also add a genuine gauge singlet now, but not just a standard model gauge singlet, but it might be a gauge singlet under a left-right symmetric model or even SO10. And if you now look at the mass matrix, which is now 3 by 3, of course more than that when you include families, but in the one family case, 3 by 3, you see when you look at the scalars that you need to generate these various terms in this matrix, you see that you can simplify life. Let's look at SO10. So rather than introducing the 126, which is what you have to do in the standard type 1 seesaw mechanism, you can now get away with just adding 16s. So you may like that. Putting in the mass scales, this 3 by 3 mass matrix looks like this, and there are two famous special cases. First one is the inverse seesaw. That's when you put ML equal to 0, but you have mu non-zero. In this case, the seesaw formula involves typically a double suppression, so mu is a small parameter which violates lepton number explicitly, and you may also have a small ratio m over mr. An advantage of this, there are two advantages of this. One is the scale of new physics can be lower. It can be TeV scale, and that makes the theory more testable. Secondly, the sterile admixture can be relatively large, and therefore this also makes the production of these heavy neutral lepton states more plausible. The linear seesaw has mu equals 0, but ML non-zero, and similar comments. All right, so these two things, the inverse and linear seesaws, produce small m nu without tiny neutrino Dirac masses, and with a low scale of new physics, and are therefore more testable. The price you have to pay is introducing technically natural but small L-violating parameters, either mu or ML. Are they improvements over regular Dirac neutrinos with a coupling constant of 10 to the minus 12? Well, I think if you plug in the numbers, you convince yourself that they are, in fact, improvements. So it is very well motivated to search for heavy neutral leptons of one sort or another related to neutrino mass and or leptogenesis. There are a couple of talks on experimental possibilities here, ICHEP and FCCEE at this meeting, and there are a lot of theory papers about it, and I quote some of them here. Now let me turn in the final part of this talk to radiative or loop level models, something I've worked a lot on. So what you do is you start off with one, I think, comprehensive and systematic and well-defined strategy is you start off with effective operators, non-renormalizable ones that gauge invariant, but that violate lepton number by 2 units like the Weinberg operator. But there's not just the Weinberg operator, there's a plethora of these sort of operators. And then you open it up, you derive it from an underlying renormalizable theory in the UV, and you produce neutrino self-energy and mass at loop level. So this provides a systematic model building and classification procedure. There are two complementary approaches that have been pursued in the literature. One by the Valencia group involves opening up Weinberg-like operators, and then the Melbourne group, my group, which looks at non-Weinberg operators, and these are complementary. And there were many talks on these sort of approaches and models in this meeting. So for an example, here's a delta L equals 2 effective operator. Here is one way to open it up. It involves two scalars, a singly charged and a doubly charged scalar, and here you can turn it into a loop graph for a neutrino mass at 2-loop level. This is the reasonably famous Z-Babu model. And the point is that these exotics, or one point, is that these exotics K and H can be searched for at the LHC. So these radiative models come with all sorts of other new physics, which is usually very searchable. So, rich phenomenological implications. There are connections with many other areas of physics in these radiative models. There's a connection with dark matter, I'll mention that briefly, charged lepton flavor violation, even quark flavor physics. Collider searches for exotics, I've just mentioned that. Also, G-2, electric dipole moments. So here is a dark matter connection. This is the famous scotogenic model of Ernest Marr. So it involves a one-loop generation of neutrino mass where the dark matter candidate, which can be either this guy or that guy, occurs in the loop. So it's called scotogenic because that means created from darkness. So it means the neutrino mass is created from the dark matter mass, which is kind of interesting. With a former student, Gargalionis, we did a survey of all of these radiative models. You should do a survey because there are many of them. We concluded that there are more than 10,000 reasonable or plausible or possible models, maybe not all plausible, possible models just involving scalars and fermions. And we did a survey of what sort of exotics you get. So here is a survey of all the scalars. You get leptoquarks, that's the dominant type of scalar that you get. You can get diquarks, dileptons, and a bunch of other things. On the fermion side, you've got vector-like quarks that dominate the counting, vector-like leptons, and then others. And these exotics, many of them, are interesting for other reasons. For example, S1 and R2 are two leptoquarks which appear in these radiative models. They're of great interest for the RD star anomalies. Used to be of interest, another one used to be of interest for RK star, but RK star disappeared from the slide. My tears kind of washed it away when we found out that wasn't true some 18 months ago. In any case, and G-2, it's also relevant for that, EDM, etc. Anyway, whether any of these anomalies are true, the point is that these exotics give you some sort of effects in flavor physics involving quarks and or charged leptons, and there are a lot of exotics you can search for in colliders. You can also work out which exotics occur together. So if we were ever to discover an exotic in a collider, and we discovered two exotics, and we found that they were just, for example, these guys here, we would know that these go together in many models of radiative neutrino mass generation. Okay, let me now close. You can read, I won't reiterate things I've already said, but let me close with reasonable things to hope for on the experimental side. A positive neutrino-less double beta decay signal would be wonderful. The search for low-mass, heavy neutral leptons is highly relevant. Charged lepton flavor violation is very important. And then deviations in G-2, non-standard model quark flavor effects, maybe they will one day be confirmed, and a search for exotica at future colliders. Thank you.
Okay, thank you again for this very nice overview. Questions? Yes, already. Okay, 2.
Thank you so much. Would the confirmation of proton decay, be it supersymmetry or not, serve as an angel to neutrino mass?
Proton decay. I would say not necessarily. Of course, the discovery of proton decay would be, you know, a fantastic thing. I think not necessarily directly connected with neutrino mass, but would certainly point us in the direction of some kind of BSM physics. And when we go in that direction, maybe there will be something that we discover also about neutrino mass. I mentioned that one of the exotics you have are diquark scalars, and certainly diquark scalar interactions can violate baryon number. So I would say, off the top of my head, there's a possible connection there.
Okay, Maruyama-san?
I have one comment and one question. The one quick comment about testability of high-scale seesaw theory is the potential gravitational wave signal coming from cosmic strings.
Okay.
And higher the scale, the bigger the signal.
Yep.
So in principle, you can measure the seesaw scale and show that there's a new energy scale in nature.
Okay, good comment.
And second point is a question. So you made a remark that even the original beam and tau masses are not verified, given that LHC has measured the coupling, Higgs coupling to tau in the bottom.
Yes.
I wonder what you actually meant by that.
Yeah. First of all, thank you for the comment about gravity waves. I think you know, future gravity wave observations, particularly space-based ones, are becoming extremely relevant for BSM physics, and I think that's a growing area, so thank you for that. Now, the B and the tau couplings to the Higgs have been measured at the 10% plus or minus a few level. It turns out that is not precise enough in order to rule out a radiative origin for those two particles. The only thing you can say is probably you need Yukawas of about, you know, order 1. So future measurements, which may get the precision down to 1%, will require Yukawas to be a little bit higher. But it was interesting to me that that this possibility is not ruled out. And in fact, I think that's an important and neglected question.
Ah, interesting. That's a good case for Higgs factory.
Okay, Professor Shin.
Very nice talk. Usually people argue that neutrinos are very special because they are the only electrically neutral fundamental fermions in the standard model, and their masses are too small. So in this case, there must be very different mass generation dynamics.
Yes.
But from your overview, either the seesaw models or the radiative models, all these models have the Higgs fields or the scalars. So does that mean the scalars or Higgs fields must be responsible for the generation of tiny masses of neutrinos, and perhaps also for other dark particles, dark fermions? Is this the case?
Well, for dark fermions, no, I don't think the Higgs has to be involved at all. I mean, in the case of neutrino masses, since we're talking about left-handed neutrinos, which exist in a weak isospin doublet, then electroweak symmetry breaking is involved at some level. It may be the Higgs doublet itself, or it may be in, say, type 2 seesaw, a Higgs triplet. But one way or the other, certainly electroweak symmetry breaking has to enter into the scenario at some level.
Okay, very last one in the middle. Microphone.
Sorry. In your second point, a low mass, heavy neutral lepton.
Yes.
What is the mass scale you are talking, and what is the significance?
Yeah.
Why you want this?
So I think okay, I'm not an expert on this. In the case of something like the new MSM, this thing I mentioned, which is the seesaw Lagrangian, but with very low masses for the right-handed neutrinos, in that scenario, to get that to work, you need one of the right-handed neutrinos to be several keV, to be sterile neutrino dark matter, and you need the other two to be GeV scale in order to get baryogenesis to work. So we're talking about K V-scale, G V-scale sterile neutrinos, and that's where you can search for them in the decays of mesons. Okay? And so the SHIP experiment is all about that. In some of the other cases, like inverse seesaw, we are probably talking about T V-scale sterile neutrinos.
Thanks.
Okay, so let's close the session here, and thanks to all the speakers in this session. And there's an announcement.
So quick announcement from the organizers. We are going to take the conference photo now. The conference photo will be taken outside of the conference center, so just go out through the main entrance, and there you will see volunteers to direct you. After the photo, there will be a coffee break, 30 minutes. So please now move out and we take the photo. Thank you.